When we hear the word Cosmodrome, we usually picture something like this. And no matter how many times you've seen it, it's still fascinating. Stop! But the launch of a rocket is just the culmination of everything that happens here. And the rocket site. The rocket site is just a small part of a huge complex of facilities with a sophisticated infrastructure covering an area equal to some European capitals. I doubt there's even one know-it-all out there who knows exactly how many Cosmodromes exist today. Nowadays, they can be either mobile or stationary, secret and open to tourists, active and decommissioned, experimental and commercial. Today, things are happening that once only science fiction writers talked about. Planet Earth has turned into the starting point for all humanity. Right now, try to guess approximately how many Cosmodromes there are on Earth. 3, 5, 8, maybe 15. No, there are 34. 25 of them are Cosmodromes located on the Earth's surface, more precisely on land. The remaining 9 are at sea or mobile. And of course, almost everyone knows the world's largest Cosmodrome. It's located right here. The translation of its name from Kazakh, Rich Valley, isn't mentioned very frequently. But even without a translation, this name has still gone global.
Baikonur sent man into space.
Le Cosmodrome de Baïkonour.
Байконур 发射场
Actualidades en Baikonur.
Прахи Байконур.
Мы в Байконуре готовят к старту Байконура. Байконур.
Earth's first artificial satellite was launched right here. Yuri Gagarin said his blast off. This is the launch pad of the Proton heavy carrier rocket. Plus an infinite number of other records, dates and events on a global scale with universal significance are connected with this place.
Добрый день. Начинаем.
Baikonur is the first Cosmodrome to ever send a man into space. To date, there are only 3 such places on Earth, even after almost 60 years. America's Cape Canaveral and China's Jiuquan. However, there have only been 10 Chinese astronauts so far, which they call taikonauts. From America, that figure reaches 126. But there have been 350 people who have gone into the orbit of our planet from Baikonur. Now, as the saying goes, all eyes on the screen. This is where Gagarin launched at the Baikonur Cosmodrome. This is Site 43 at the Flesets Cosmodrome. This is Site 1C at the Vostochny Cosmodrome. This is the Soyuz site at the Guyana Space Center. Can you see any differences between them? That's right. There's almost no difference. But why is it that there's practically no difference? In terms of ballistics, the bullet is an ideal object for flight. But whoever thought of designing a bullet first, and then creating the weapon that's supposed to shoot it? With Cosmodromes, it's the opposite. Launch pads always conform to a specific rocket. And if, say, the Soyuz should take off from different sites, then they will be identical, except for the landscape surrounding them. That is, from the point of view of space aeronautics. It's not a bullet made for a machine gun, but a machine gun designed for a bullet. And even more than that, all the world's cosmodromes in fact differ very little in terms of their design. What are cosmodromes made of? In a simple, structured sort of way. This explanation can even be understood by, well, you know what I mean. May I? Here is the start or launch pad, the site where the rocket takes off. ATB is the assembly and testing building where the rocket is assembled before launch. And CP is the command post, where you hear the famous 3, 2, 1, ignition, blast off. 3 facilities. What could be simpler? These are the main ones, but in reality, there are way more facilities at any modern cosmodrome. Weather station for accurate weather forecasts, aerodrome, seaport, railways, sometimes all in the same place, to receive cargo and disassembled carrier rockets, military unit to guard facilities, a town or nearby city, since a cosmodrome staff has to live somewhere, a plant producing liquid oxygen, which is necessary to launch a rocket, a system for the reception and storage of liquid oxygen, a system for the supercooling and thermostating of liquid oxygen. Stop. But why do you need liquid oxygen? When we refuel our car, we often forget that gasoline or diesel is only half the fuel needed to run the engine. The second half is for the inhabitants of Earth, as natural as it gets. What we never really think about, what surrounds us at all times, and what is in short supply in space, where rockets are launched. This is oxygen. If you try to start a fully fueled car outside of Earth's atmosphere, it'll never work. Without oxygen, no internal combustion engine works. Flight Control Center, Flight Control Center. We have a problem. Where's the oxygen? Where's the oxygen, I said? So any rocket launching from a cosmodrome carries 2 fuel components in its tanks, a fuel and an oxidizer. Oxygen is a very powerful oxidizer. After all, combustion is basically the rapid oxidation of fuel. Wood, for example, with the release of light and heat. There is 21% oxygen in the atmosphere of the Earth we breathe, 1/5 of its volume. And if that number is 100%, as in this flask, combustion reaches its maximum capabilities. But no, this still isn't the limit. Liquid oxygen, gas, cooled to minus 183 degrees Celsius. At this temperature, it turns into water, very cold water. And that's what happens if you combine this superoxidizer with any fuel. By the way, this is an ordinary piece of bread. During evaporation, liquid oxygen increases in volume by 800 times. That is, in 1 liter of this substance, there is the same volume of the oxidant as in 800 liters of gas. Liquid oxygen, a superconcentrated oxidizer, provides the most powerful burning rate for any type of fuel. If you look at the Soyuz in its cross-section, it's obvious that the rocket is no more than a flying fuel tank. Out of 307.5 tons, 307,650 kilograms of the total weight, almost 274 tons, 273,900 kilograms, is fuel. And most of the fuel is not kerosene, but rather liquid oxygen, 190 tons. Remember this, it's extremely important. If we didn't learn how to compress oxygen with the help of cooling, we'd have to send a bloated monster like this into space. Now the question: where does this much-needed aeronautics liquid oxygen come from?
Жидкий кислород.
Academician Piotr Kapitsa, Nobel Prize winner for his study of the superfluidity of liquid helium. But the physicist's interests went way beyond that, from plasma and thermonuclear reactions to the hydrodynamics of layers of a liquid. And in 1945, Kapitsa founded the Special Institute of Oxygen Engineering and the Balashikha machine building plant, which was commissioned in 1949. Later, they were merged and renamed Cryogen MASH. The company is a member of United Heavy Machinery Plants. Cryogen MASH production equipment is supplied to more than 30 countries around the world, including the USA, India, and South Korea. It operates on 1/3 of all Cosmodromes on Earth, refueling and thermostating systems, stands for testing rocket engines, thermo-vacuum and high-altitude cameras. These are all products Cryogen MASH supplies for Cosmodromes. 70% of all technical gases in Russia are produced using equipment manufactured here, including liquid oxygen for the domestic space industry. And not only for production. Storage, refueling, and transportation for this cryogenic supercooled gas. This is all a unique system, not just for Russia, but for the whole world. Global coverage and a professional approach is a trademark of United Heavy Machinery Plants and Gazprom Bank, the industrial bloc of which includes UMBP. Space aeronautics is one of its most promising business areas. The path there for both industry and all of mankind began long before 1945. This young man was very fond of music. In his childhood, he dreamed of becoming a composer, but he was born in troubled times and in a very troubled country. In the 1930s, the young man joined the military, and he started to design ballistic rockets for Germany. The name of this unsuccessful composer was Wernher von Braun, and the name of the rocket he created was the V2. The V2 was the world's first long-range guided ballistic rocket. It also became the first object ever to make a suborbital spaceflight. But it had nothing to do with peaceful space exploration. The V2 was launched to bomb the United Kingdom. It targeted the densely populated areas of London. After the war, von Braun fled to the United States and became the father of the US space program. Meanwhile, the Soviet Union was hard at work developing its own rockets. The drawings and details of the German V2 fell into the hands of a talented Soviet engineer. He was particularly fascinated by the engine and propellant components. There were two of them in the von Braun rocket: ethyl alcohol and liquid oxygen. Sergei Korolev created on this basis a fundamentally different rocket. Instead of alcohol, he used kerosene, which increased power by 30%. He also introduced the concept of the first and second stage. The pinnacle of his work was the R-7 rocket. In fact, it was ahead of von Braun's developments in the US. This accomplishment is still held in high regard in modern Russia. The R-7, renamed, modernized, later to the Soyuz rocket, still launches successfully from the Baikonur Cosmodrome today, and from the northernmost Plesetsk Cosmodrome, and from the new Russian Vostochny Cosmodrome near Blagoveshchensk, and from the Guyana Space Center, the closest cosmodrome to the equator. To this day, the rockets taking off from these sites carry kerosene and liquid oxygen in their tanks. So somewhere near the launch point, there needs to be a gas station. You already know about kerosene. It's manufactured as a petroleum byproduct. But what about liquid oxygen? Where do we get that from? We can't just grab it from thin air. In fact, that's exactly what we do. Any other method is too expensive and inefficient. The nitrogen-oxygen plant in Baikonur, a facility that's rarely mentioned. But without it, there would be no space exploration. The tanks of each Soyuz vehicle taking off from Baikonur carries about 200 tons of liquid oxygen. This is more than 140,000 cubes of gaseous oxygen. The volumes are huge. Its operation is ensured by two devices, a very powerful vacuum cleaner and a very large refrigerator. Okay, I'll explain in a bit more detail. These are plants for the production of industrial gases. Here, it's easier to show how they work. Air from the atmosphere, meaning literally from outside, is pumped in and compressed to 6 atmospheres using a compressor. Once in the UCT, the unit of complex treatment, it is stripped of its carbon dioxide, hydrocarbons and moisture. After passing through the heat exchangers, the air then expands in the expander machine and throttle valves. As a result, it's cooled to a temperature of minus 180 degrees Celsius. Further air separation is then based on the different boiling points of its components. Oxygen, minus 183 degrees Celsius, 90.18 K, and nitrogen, minus 196 degrees, 77 K. For the final stage, we'll head over to a working plant. This is the cold block. It's where distillation columns are housed. In the process of air separation at cryogenic temperatures, mass and heat exchange is carried out between the liquid and vapor phases in contact. Nitrogen concentrates at the top of the bottom column and oxygen-enriched gas at its base. In the upper column, the air undergoes its final separation and the production of pure oxygen. 1 cubic meter of oxygen is obtained from 5 cubic meters of air. Modern plants take 25 hours to produce 190 tons of liquid oxygen, enough to refuel a Soyuz rocket. We'll leave from Samara. Samara. There it is. We'll transport it to Plesetsk. That's not so far. And then we'll go from Samara to Blagoveshchensk. From Samara to Blagoveshchensk. There is Blagoveshchensk. That's quite a ways. Sometimes we go even farther. Missile carriers, Soyuz, made in Samara, are shipped in containers to Baikonur, to the Vostochny Cosmodrome, and even to places without any railways. The Guyana Space Center is on the other side of the Atlantic. Soyuz rockets are shipped there on special rocket-carrying ferry boats with the names of birds: Hummingbird and Toucan. But no matter how or what model of rocket is delivered to a Cosmodrome, it is immediately sent to the ATB upon arrival. The Assembly and Testing Building, in short, the ATB. This is the hangar where the rocket and its head is assembled and tested. Any modern Cosmodrome has similar buildings. Here we are at Baikonur. This is the Guyana Space Center. They do not differ significantly from their international analogues, except for one essential detail. When a rocket is assembled horizontally, the ATBs look like hangars. But when assembly is vertical, they look more like high-rise buildings. Here is one of those types. This is where the European Ariane 5 carrier rocket is assembled. Looks impressive, but in terms of its functionality, it's the same as an ATB. It also has its own three-letter name: the Launcher Integration Building, abbreviated LIB. The difference in approaches is an eternal argument about which is better. Vertical assembly of a rocket is more difficult. It requires tall buildings. Besides, carrier rockets are always transported to the launch site vertically. Looks epic, doesn't it? But from a technical perspective, it's a massive headache. But on the other hand, this way you don't have to add resistance to horizontal loads when designing the rocket. But most important are the requirements of the spacecraft manufacturers, who can make certain demands about their products. That is, a satellite or vehicle cannot be stored and transported other than in a certain specified position. For example, strictly vertically. Most people see a rocket and its cone as a single unit. In reality, a carrier vehicle can be compared to a taxi, and a space module would be like one of its customers. If the latter has any wishes and complaints, the driver has to take them into account. But how can work be carried out if almost all domestic rockets are assembled and shipped to the launch site horizontally, and only then are they raised up? To solve the problem, this construction was created: a mobile maintenance tower. So that's how the whole system works. The rocket is brought to the launch pad without its head. Then it is set up vertically. The tower drives over it, and inside, a satellite is installed on the rocket. Thus, the customer's requirements are met. It is not turned over before being launched into space. Only after all the checks and a few hours before the start is the rocket filled with fuel. Here it comes. The most precarious moment. The Soyuz is painted mostly with grey paint, but it takes off all white. Watch any video, it catches the eye. This color change is caused by liquid oxygen. Once inside the rocket tanks, it quickly cools everything around it, so the outer surface of the Soyuz is covered with frost. In any weather, even at sub-zero temperatures, where there used to be a grey rocket, now there is a white one. When I was a child, my grandfather once asked me, "Are we human because we flew into space, or did we fly into space because we are human?" My grandfather was fascinated by space and Gagarin. Only now I realize what he meant. Rockets aren't just engines, fuel, a launch pad, although all this is necessary. Rockets are a dream. A dream about something else, about something bigger and better. Mankind built a gateway into a dream in less than 100 years. Cosmodromes. They're all the same, but each of them is unique. There are thousands of people standing behind each of them, like you or me. Well, not exactly like us. And even though they've accomplished a lot, there can still be no doubt the dream is alive even today.